Alright, so we have an implicit differentiation type problem. There's no differentiation written here yet, but this is a curve in the xy plane. And so what we're going to do is we're going to first verify that this point lies on the curve, and then we're going to figure out an equation of a tangent line to that curve at this point. Right, so let's first verify that this point lies on the curve. And so this is, you should read this as xy coordinates, and so this is 4 cubed minus 9 times 4 times 2 plus 2 cubed, and we should just see what that is. Let's just see what that is. And so we get 64 minus 72 plus 8, which is negative 8 plus 8, which is 0. And the fact that this, when we plugged in 4 for x and 2 for y, and we got 0 on the left-hand side here, this verifies that this point, these values for x and y satisfy this equation, right? So the point lies on the curve. And now the second part is determine the equation of the tangent line to this curve at the point 4, 2. Let's just see what happens. Alright, so this is an example of implicit differentiation. We have now added to our toolbox the ability to differentiate both sides of this equation with respect to a variable. And so you need to be thinking that, while y might not necessarily be a function of x, in fact, if we graph this curve, we'll see that this does not, in general, define y as a function of x. This particular curve fails the vertical line test. We get something that looks roughly like this. I'll just draw a quick little sketch of it up here. Something that looks roughly like that. And so it fails the vertical line test. However, in little bits and pieces, we do get that y is a function of x. And so actually what we need to do is we need to treat y as a function of x, and we need to think about differentiating this equation implicitly, because this implicitly defines y as a function of x in pieces. All right, and so what we're going to do is we're going to differentiate the curve with respect to x. And so we're going to differentiate the left-hand side, and we're going to differentiate the right-hand side. And all the while you should be telling yourself, y is a function of x. Y is a function of x, over and over. Just keep telling yourself that, right? And so on the right-hand side, we differentiate 0 with respect to x, and we get 0. That's fine. On the left-hand side, we differentiate each little piece with respect to x. So x cubed, we get 3x squared. We differentiate 9xy. This is a product here with a constant multiple out front, and so we get minus 9 times a derivative of this product. And so if we differentiate x, the derivative of first is 1 times y, the value of the second, plus the value of the first, x, times the derivative of the second. So now remember, we're differentiating with respect to x, not y. So when we differentiate y with respect to x, we get dy dx. And then similarly here, y you should be thinking is a function of x. And so think of this as the chain rule. The inner function is y, which is a function of x. The outer function is the cubing function, and so we get plus 3 y squared, and then from the chain rule, dy dx. Right? And so, right, we can multiply this out, and what do we get? We get 3x squared minus, let's see, 9y plus, not plus, we got to distribute negative 9 through to both, minus 9x times dy dx plus 3y squared times dy dx. And what we're looking for here is we're looking to get to write down dy dx as an expression in terms of x and y and some constants and such, right? And so what we would like to do is just isolate everything with dy dx on one side, and think of it as solving any other sort of linear equation. We need to get this quantity by itself, and we're going to factor it out, and then we're going to divide. So you'll see what I mean, I hope. And so let's see. Everything without dy dx, we're going to move it to the right. So we're going to subtract 3x squared and add 9y on both sides. Right. So on the left, these go away. We get negative 9x times dy dx plus 3y squared times dy dx is negative 3x squared plus 9y. So that everything with dy dx in it is on the left, everything without is on the right. Okay? And then now what do? We factor out a dy dx on the left-hand side, and we have dy dx times negative 9x plus 3y squared is equal to negative 3x squared plus 9y. So we factor out a dy dx. And lastly, we divide both sides by this quantity here. Right? And so on the left, a number divided by itself is 1. And on the right, this is their expression. So what we end up with is dy dx is negative 3x squared plus 9y, or negative 9x plus 3y squared. All right, so dy dx is a function of y and x. So how do we use this? Well, remember our goal is to find an equation of the tangent line to this curve at the point 4, 2. So you've got the derivative here, dy dx is this. And so we would like to evaluate this. And so I'm going to write, here's some perhaps new notation for you, perhaps not. I'm going to write this with a vertical bar. This is going to mean evaluate. So we're going to evaluate the derivative at xy equals 4, 2. And if we plug this in, so now we're going to plug in 4 for x and 2 for y, so we get negative 3 times 4 squared plus 9 times 2 over negative 9 times 4 plus 3 times 2 squared. Okay. And so if we simplify this, or if we multiply this out, let's see, that's 16 times negative 3 is negative 48, I believe, plus 18, divided by negative 36 plus 12. Right? And so that's negative 30 divided by negative 24 is, let's see, not 6 over 4, what is it? So we can cancel 6 and everything, so we get 5/4, positive 5/4, right? And so now we use the fact that we know what the derivative is at that particular point. It's 5/4, and we have the particular point. So the equation of the tangent line is y minus the given y value, which is 2, is equal to 5/4 x minus the given x value, which is 4. And that's the equation of our tangent line.